name is Christopher Cameron. I'm presenting an introduction to modern R data analysis today. I am a computer scientist or computational scientist at Cornell Center for Advanced Computing. So today I'd like to address a few things. What is R? How does it fit into the statistical analysis and data science ecosystem? And when is R a good choice? Who should be using R? What features make R useful for researchers? And where can you get more information if you want to use R for your own work? I will say that R takes time to learn, and for many of you, this might be your first step towards R. So the materials and demonstrations today are designed to help you decide if R is worth investing your time in learning. So R is good for tabular data, like vectors or lists, or the kinds of data tables you might have in Excel. It's great for statistical analysis. It's good for data visualization. And if you have custom code that's written in C or Fortran or Java, R can make a good front end to that code. R is less suitable for unstructured data, for scripting your file system, or for data scraping, cleaning, and formatting. That's a caveat there. It's not that great for cleaning and formatting unstructured data. It's great for cleaning and formatting data that's already in a tabular format. There are some people that want R to do everything, so packages do exist, and new packages are released all the time that help R address some of these areas. But at this moment, it's not too good for unstructured data, pretty bad at file system scripting, and mediocre, I'd say, at data scraping, unless it's already tabular data. R is part of a trio of modern open source computer languages that are favored by data scientists. You may have heard of Jupyter Lab. I'll be talking about that next week. But it's actually named after Julia, Python, and the R languages. R and Python have significant overlap. They might appear to be competitors. And many people just use both because each language has its strengths, and you do some work in R and some work in Python. Python is a more general language. It tends to be favored for deep learning. R and Python are both very popular for machine learning. R tends to be favored for statistical analysis. Both of these languages have huge communities and are supported by many add-on packages. Julia is a general purpose language. It's relatively new. It's influenced by both R and Python. It's something to keep an eye on. R is a relative newcomer to the statistics software ecosystem. There's been some software in use today that was developed in the 1960s. That even though R is relatively new, as is Python, R draws on some languages that have been around for a long time. So it has a long legacy, even though it's a relatively new program itself. And this shows some of the influences on R and influences to Python. You see that R and Python share some influences. And in turn, Python and R influence Julia, who also draws inspiration from MATLAB. So R came about because two faculty members at the University of Auckland wanted better software for their teaching laboratory. They didn't like the commercial offerings available. They did like this S statistical programming language that they'd used, but they wished that it had some modern language features that they saw in a Lisp variant called Scheme. So they put together their own implementation of S. They called it R, and they added the Scheme features that they wanted, and they distributed it to their colleagues via email. And after a few years, a colleague had persuaded them to open source R, and that's where R comes from. So this, I tell you this because this is sort of the story of how R development proceeds even today. It's people who like something, they wish it had this other feature too, so they'll combine them together and share them. That means that R's development is both collective and eclectic. R's developers will borrow code conventions and programming styles freely and combine them together into something that is focused on practical and productive use. You'll notice many conventions are followed in R code. R doesn't require those conventions, and those conventions don't have any special meaning. So you'll see, oh, this part was written probably by a Java programmer because they're bringing up a lot of Java conventions. This one was written by someone that came from Python. R is written by its users, and they bring a lot of themselves to the development. A great thing about R, probably the best thing about R is its community. It's used and supported by academic researchers and more recently, data scientists and the companies that employ them. R gains new features via packages that are developed by the community. Today, there's over 10,000 add-on libraries to R. These packages target highly specialized research areas or cutting-edge methodology. I've linked some things for you to look at later. One is the official package collection at rproject.org. There's other large collections, Bioconductor being one of the major non-CRAN collections. You can also load packages directly from GitHub. So if you're an author who's developing a package and you don't want to meet the standards of CRAN standards it's required that the package will work on all the platforms R supports. Some people develop packages just for themselves or their lab, and they'd like to share that. So you can share it directly from GitHub. Aside from this development community, there's a large community of people who are developing tutorials and demos for R, and I've linked some of the good ones here. I'll call out our Cornell Virtual Workshop in R complements today's materials. That virtual workshop focuses on using R in a parallel computing environment. Another really strong feature of R is its documentation system. It's among the best documentation systems I've seen in for a statistical analysis program. A typical help entry will include descriptions of each function and their arguments. It'll have examples showing how the function might be used. And then the great thing, because it was written by academics, is that it will include references to relevant manuals and the academic papers where these methods were developed, introduced, and discussed. So you can learn a lot of statistics just by reading the references sections of our documentation. When you have a package that you've downloaded, usually that will include a vignette, which is a way of, it's a narrative demonstration of how to use this package to do the intended type of analysis. So it'll be how to use this package to do some type of analysis. And it'll be bundled with data sets that support that vignette, and they demonstrate the required data format for that particular package. It's a great way to learn R. It's easy to overlook the documentation, but it is a wonderful resource. And it's almost as good of a feature as R's community. Base R is distributed by the R Foundation. It is a command line interface that you access via an R console. So you literally type commands, press return, it creates objects in memory. You can manipulate these objects interactively by typing more commands. So R is interactive, but maybe not in the point and click graphical user interface sense that you're probably used to. Most people that use R don't use the plain R console directly. Instead, they usually use something that interfaces with that R environment. The popular choices, the RStudio IDE, which we'll look at today, Jupyter Lab Notebooks, and Google Colab, which is a cloud-based notebook that can access R. Here's an example of the R console. It's pretty plain. It's a window with a console. You type your commands here. RStudio is an integrated development environment for R. It was originally developed by the RStudio Public Benefit Corporation. They have recently changed their name this week to Posit. So RStudio and Posit are the same thing now. They've promised that all the old links will still work, so all the links here will continue to work. RStudio uses whatever version of R you have installed. So when you're going to use RStudio, you have to install R first, and then you install RStudio. RStudio has a very nice cloud version. It's free to use for a limited number of hours each month. It's a cloud-based version of RStudio that they did a really good job making the interface for RStudio Cloud match the desktop application RStudio. So if you want to learn how to use RStudio without having to do any installation, you can go to RCloud, sign in with your credentials from GitHub or Google, or sign up with them directly, and then you can use a hosted R instance. We'll take a look at the RStudio interface in more detail today. Essentially, it still has that console, but they've added some additional panes that people find useful. I'll flash these up here for you to go back. You can freeze frame these and get the URLs off here, or maybe we can distribute these later. We have our workshop. There's great cheat sheets. A really nice example of using R for teaching and for research can be found at Chris Bale's teaching website. There's some great ebooks for R and a little bit of information about how to install R for Jupyter Notebooks. At this point, I'm going to switch over to R itself so we can get started on some demos. Okay, you should all be seeing my RStudio interface. I would not recommend using Google Colab to process data that might be sensitive. Talk with your IT folks about an appropriate environment for data that is sensitive, because it is up on the cloud. Yeah, so that entails a certain amount of risk. So check with your IT folks about their policy and make sure you stick with it. So you should be seeing my RStudio interface. It's the main portion of the window is the R console. There's a few important panels on the side. One of them is a file browser. It's a pretty convenient way to access the files that are associated with this project. The other one is the environment viewer. If you're coming from something like Excel or SPSS, you are used to seeing the things that you make with the program, that you run analysis and you see the results. In R, it doesn't print it out automatically. It creates objects in memory, and you need to manipulate those objects and ask for the information out of them. So it'll create things in memory. You'll be able to see that R is doing things because you'll see objects appear in the environment. It's more reassuring if you're coming from a background where you kind of expect more visual output to see that things are happening in the environment, even though you're not getting a lot of printout. So initially, one way to use R is literally typing commands in the console, press and return, results come out right there. Then next, probably more common way to use R is through a script file. I'll open one here. An R script file ends with .r. It is essentially a sequence of R commands interspersed with comments. Comments start with a pound character. I can highlight or put my cursor on a line, use the run command to run that line. I can step my way through a script running one line after the other. It's a convenient way to make a history of the commands you use. It's not that convenient to run it interactively because the command is up here and the results are down here. And so you need to continually flip your attention back and forth between what's in the script and the results that it's produced. And so it's sometimes this is the only way to use R in systems without a graphical user interface. This is a good way to produce a sequence of commands. You can execute a script and have it produce a result. When you're using R interactively, it's nice to have a history, but it would be nicer if your results and your commands were more tightly coupled. And it's also, the comments are not they're okay, but they're not a great way to explain what you're doing. So you have to fit anything you want to express to document your code, you have to express it through the comments. And I think that what most people do now is use a different format called Rmarkdown, which I'll show you next. I'll show you the short version. So an Rmarkdown is a different format. It uses a version of Markdown, which is a plain text formatting Markdown that is R aware and R friendly. It's different from a script because it's basically a text document that has special cells devoted to R code and to R results. So the R notebook is designed to support something called literate analysis that comes from the idea of literate programming. In Literate statistical analysis, you have documentation, specification, explanation, interpretation, and code, all coexisting in a single document, and it presents the analysis in a narrative format. This is a nice way to communicate with your future self when you want to come back to a project after a few weeks or months, and you want to be able to quickly figure out, remember what you did. It's a nice way to share results with other people because you can, a lot of science is explanation. It's a lot of communication, and so you can put that communication right in a notebook, along with the small bits of analysis that you need to do to actually produce your results. And when you share that notebook, someone has sort of your complete narrative, not just here's a script file and then here's this other paper that describes what we did. Let's see. Rmarkdown, you can use either Rmarkdown's. Rmarkdown has a syntax that you can use. You can type in this syntax if you prefer, or you can use the visual editor. And probably when you're reading someone else's R, you're going to want to use the visual editor. So it provides a variety of formatting options, including you can put in nicely formatted equations in LaTeX format. You can include references. This is the Markdown syntax that produces all those different formats. So if you prefer to write in the source mode, you would type these characters, and that indicates the formatting. An important thing about Markdown that's a really useful feature, I actually had revealed it too early. Rmarkdown supports headings, as does regular Markdown. Instead of these these pound signs representing comments in Rmarkdown files, these represent headers. So the top level header has one pound character. The deepest level has 6. If you use these headers to organize your document, it is hierarchy. You can view it in the outline viewer, and someone can easily see what topics are covered in your notebook. They know how long it is, and it's easy for them to navigate by jumping to different parts. So I'll jump down to this part with a code block. This is what code blocks appear, how they appear in an R notebook. This is the same command that I would have typed below, but now I can run that cell. The results appear right below it. So the command and the results are paired together. And because they're paired together and they appear in the notebook in one document, I don't actually have to have the console open anymore. So I give it a little more room to work when I'm using this format. If you're coming, so R provides a variety of math and statistical functions built in and mathematical constants. If you don't program or haven't been programming in any language that uses functions, I'll describe them briefly because we're going to use them later. In programming, a function takes an input and it returns an output. In R, our convention for calling a function is to write the name of the function followed by parentheses. Inside of those parentheses are any arguments that the function operates on or that modify the way the function behaves. So in this example, this function has one argument. If there's more than one argument, it's a comma-separated list. So for example, this is the log function with an argument of 10, saying take the natural log of 10. There's also a version of log that takes additional arguments. You might not know what that does, and that's okay because you can find out what it does by using the documentation. If you start a line with a question mark and type the name of a function, it will open the help for that function. So scrolling through this help, I can see, oh, there's a version of log that takes 2 arguments. The second one is the base. So instead of the natural log, I can take the log base 10. Notice that this argument has a name. When you're using a function in your code that accepts a named argument, go ahead and put the name there right in your code. So this will do the same thing as log 10, 10, but now when I come back in 2 weeks, if I don't use a log function often, I know exactly what this function does. I know that the second argument refers to the base because the name is right there in my code. it's good practice. There's some functions that take a dozen arguments, and it's way better to name them all so you can remember exactly what they do. A second thing that you might not be used to if you're coming from a scripting language or not coming from a scripting language is the idea of a variable. In programming, variables are used to store values and to use those values. So in R, we can do assignment with an equals sign. There's an old holdover from a keyboard from the 80s. It's an arrow key assignment. You type it with less than and hyphen. It accomplishes the same thing as the equals sign. Your organization may have a style guide. Google likes the less than hyphen for assignment. Anybody coming from Python is probably pretty comfortable using the equal sign for assignment. So I'm going to make a variable called width. I'm going to put the value 20 in it. And when I run this, nothing will appear to happen in the notebook because that's an operation that doesn't return anything. But if you watch in the global environment tab up here, you'll see that my variable will appear. So now I have a variable called width with a value of 20. I can also use variables to store the results of a computation. So now height is the result of the computation that I put into it. Now that I have these variables, I can use them just like the values they represent. So I can multiply width and height together to get a new value. Another important concept that even if you are only using Excel, like for most of your data analysis, you're still familiar with this idea that columns take a format, that they represent some kind of data. It's very important to have the right data types when you're using your data so that R knows how to treat it. So the really common data types that you'll encounter are numeric, Boolean values, like for an indicator variable. You may have some character values. More often, those strings are going to actually represent levels of a categorical variable. So you'd want that one to be a factor instead of, as we call it in R, instead of a string. You might also encounter date time. These are their most common types. We'll see some examples of that in a bit. Another concept that's important for understanding R is this idea of a data container. Data containers hold a collection of values. I'm going to only talk about one type of data container today, and that's data frames. Data frames are a familiar data format where there's rows as cases and columns as variables. It's the same kind of data that you'd normally use in an Excel spreadsheet or a CSV file, or if you're coming from pandas, like a pandas data frame. R has a built-in data frame-like structure called data.frame. There's two common variations you might encounter in other packages. One is the data.table. That's a data frame that has features to support large data analysis. Another is a tibble, which behaves very much like a frame, but it has more strict behavior that makes it better for use in scripting. The convenience features are less likely to become gotchas when you're using a tibble. I'll create a quick data frame here. So I'm going to call it data frame function. There's my start of my parentheses. It has 3 arguments. I put them on separate lines because it's visually easier to see them. It's going to have 3 variables: the ID variable, an age variable, and a height variable. I'll run that and you can see the result. So that's the printout in the console. It also created it in the environment. If I'd like, I can click this and I can view it in a little spreadsheet viewer. That's a great question about, does data frame take in null values? It will. And R has much better missing and null and NaN representation than something like Python. Pandas, if you've used pandas very much, you've probably had your, let's see, I got you in this context. I will get to both these questions. So R has great missing data handling. It's smart about it. Every type of data can have a missing version of it. It doesn't coerce your data from integers into floats if you happen to have one missing value the way that pandas does. And so yes, you can definitely have missing values in R. It does a great job representing them. And a gotcha in the context of data frames. One thing that gets people sometimes is the partial name matching. If you want to get a column out of a data frame, you can type any portion of the beginning of a name, and if there's a match, it will pull it out. That works great if your data frames were hand built and you know that you're not going to have another match at some future point. If you're you're not going to be adding a variable that will somehow match this abbreviated query, then it's fine. But if you are using it in a script where you maybe don't know what's going to happen to it next, or you don't know what's happened to it before you got it, partial name matching may return the wrong column, the unintended column. So that's a gotcha. It's a convenience feature for many people, but if in a script context, partial name matching can be a problem. And so Tibbles don't support partial name matching. That's one example of a gotcha. Real quick, so data frames, you can pull out individual rows. Say this is saying the first row, and then every column. The comma is the fact that there's nothing here is implying every column. I can pull out particular columns by using the $ operator. So this says, get me the age element out of my data frame. And you can see this is the first row, this is the first column. To create a new variable, you can just declare it and assign a value to it. So in this data frame, I'm going to create a grade variable. First, I'll put everybody in 3rd grade. Then I'll take a subset of those people and put them in 4th grade. So this is the result from the first one. It made a new column called grade. And then after I select that subset and assign it to 4th grade, there I have it. I now have some 3rd graders, some 4th graders in my data frame. Many functions in R operate on a data frame. For instance, the summary function will produce a nice overview of your data set. So for age and for height, that's a pretty nice summary. I have some nice statistics, the min-max, and some measures of central tendency. For grade, this is kind of a disappointing summary. It just says that there's 9 values. They're all character. The reason it's disappointing is because grade is really more of a factor. We didn't make it a factor. I made it a string to demonstrate this, but we'd really rather have that grade be a factor so we can use it in our analysis in the future. To change something to a factor, one way is to use the asFactor function. I'm going to send this grade, the whole grade column, to asFactor, and I'm going to assign the factor that comes out of it back into my data frame, into the grade column. And I'll produce that summary so you can see how it changes. So now that it's a factor, I get a much better summary. Instead of just there's 9 things, I get there's 4 3rd graders and 4 5th graders. Sorry, 5 4th graders. This summary is more useful because we had the right data type. These data types really matter. It's the first thing you should always check when you load data into R. All right, that is the absolute minimum R that you need to have a grasp of before we look at the 2 modern data analysis packages that I'm really excited about. I like them. They're fun to share. Once you learn how to use them, it's a whole different way of using R than if you learned how to use R in the past before these were out. So I will put out examining data. Okay. The first thing you may need to do if you're trying to run this at home is to install your own packages. I put a little cell here with an example of how to install the Tidyverse, which are both of the packages we're going to look at today are from a collection of packages known as the Tidyverse. Before you can use packages, you need to load them. I like to use the require function. You'll also often see the library function. The advantage of require is that it checks first to see if you've already loaded it. And it won't load a second copy. Library will keep loading a copy every time you request it. It means that your memory, you may get several versions of a library loaded in memory. So I prefer require. I think everyone should prefer it. I'll run that. We'll see our progress bar on the side. It's done. Okay. I'm going to clear this environment because we don't need these things hanging around. Let's take a look at loading some data. This is probably an extremely common way to load data into R. It's a CSV file. I'll open it up real quick so we can view it. So here's my CSV file. It has a variable called registration space time. Notice that space there. And another variable called the organization. This is the registration times for this workshop. These are not particularly ordered, so we'll have to take care of that when we look at the data, but this is a list of all the registrants. The registration times, all of the identifying data has been stripped. So I'll run this and we'll take a look. Notice that there was no output. This can be upsetting if you're not coming from a scripting background. We do see that it did create this object in memory, this data frame object, and we can view it now that it's loaded right over here. But just looking at the output that R produces, it might seem like nothing's happening. And that's something to get used to R. It made something in memory. If you want to do something with it, you have to do something explicit. You have to ask it. Some things we can do with that data frame, we can ask about the names, or we can ask about the dimensions of the data frame. Looks like I already ran that cell. Get better. I'm going to clear those outputs so we don't reveal too much. I'm going to highlight this cell, run. Okay. Here is the summary of the data frame, just like we used before in the simple example. You'll notice we have a registration time variable. Its name changed. It's no longer registration space time. It is now registration dot time. That's an important thing to note about R. It does not like spaces in your column names. If you try to import one with a space, it'll automatically convert it to a different character. I believe always a period, but I wouldn't be surprised if there were situations where it used a different character. But so my variable is now registration dot time, and my other variable came in as org. I still have the same number of cases. Everything is in character class. We can look at the first few rows using the head function that prints the first 6 rows. We know that we have the wrong data type. Registration time should be a date time, not a character, and organization should really be a factor. There's a great package called Literate. I believe it's part of Tidyverse. If not, it's associated with it. It has a variety of functions with very, I think, easy to identify names. This is a function that will extract a date from a string that's in the year, month, day, hours, minute, second format. So that's what I have here. So I can, when I run that, what comes back is a date object. In R, most functions are designed to run on vectors, so I can pass in that whole data column, the registration time data column, into this function, and I get back a vector of dates. So it goes, a vector string goes in, a vector of dates comes out. So I'll use this function from the Literate package to turn my registration time strings into registration dates, and I'll reassign that value back to their column. And I'll also create a factor for organization. Its levels are Weill Cornell, Cornell University, and other. I specified them here, so that's their order. It can discover it automatically if you prefer. I'm using as factor, but this will turn this organization column into a factor instead of a string. So let's have a look at that now. There's a question in chat, does R uses vectors or vectors and matrices? It uses vectors and matrices and multidimensional arrays. If you take a values and you stack them together, you get a vector. If you take vectors and stack them together, you get a matrix. And if you stack matrices together, you end up with a multidimensional array. And all of those data types are available in R. We're not going to use them today. Multidimensional arrays are pretty great for R programming. You probably won't encounter them with data analysis unless you're doing time series. You may need to use them there. So now that I've changed these data types, now I'm using the skimmer now instead of the summary function. Skim is a nice alternative to summary that's part of dplyr. But you'll see that now I have one factor type column, one date time column. And skimmer produces some extra summary information. It gives me the number of missing, gives me my counts for my factors, gives me a min and max. Okay, now we have some data. Let's take a quick look at it. ggplot and dplyr are two packages that I really appreciate. That they're very different from. I started using R before they were available. They provide an entirely different way of accessing your data in R. I think some people have credited the Tidyverse, which was a collection of packages created by Hadley Wickham. They credit the introduction of these packages for saving R from Python. Before these were out, I think Python was becoming, it was increasingly dominant over R as a choice for data analysis. But this collection of packages makes R so nice to use for statistical analysis that I think it's helping R hold its own. So these are both based on a particular vision for how R can enable data analysis using an idea of grammar, which is a collection of verbs that describes how you'd like to manipulate data. This was based on Hadley's experience with data analysis, realizing that most of what we want to plot, most of the analysis we want to perform, use a sequence of pretty common steps, and we should find a way to represent what we're doing in terms of these steps so that we can describe how our data should be manipulated without having to go into all the details about exactly about doing those manipulations. So you get when you're done, you end up with a succinct description of the steps you take. In order for this to work, it requires this new operator called the pipe operator. You type it by typing % greater than %. It lets you chain function calls, and probably the best way to understand what that means is to look at what happens if you don't have a piper operator. So I start with a data frame here. I'd like to get it to a certain format so it's ready for plotting. So to do that, without a pipe operator, I can call a series of functions and make a series of intermediate data frames. So I can take my data frame and I can sort it by registration time, and now I have a sorted data frame. Then I'll take my sorted data frame and I'd like to add a column to it. So I'll use this mutate function as one way to add a column to my data frame. It's a cumulative total that I'm adding. And then I'll save that. Now I have my sorted data frame with this cumulative total variable. But now I'd like to filter that data frame further. So now I'll put that into a filter function. My intermediate result goes into the filter function. Then I filter it on my registration time. And finally, I get this data frame out at the end. So I've created two intermediate data frames that I didn't need or intend to use. It's not clear to someone coming back reading this code if are these all related? Am I ever going to use this one again? What was the plan here? It's hard to read this and understand exactly the author's intentions. Also, it made a lot of extra data frames in memory. So you might try to get around this extra data frames in memory issue by nesting your functions. So you'll call filter on the mutation of the arrangement of this data frame. The arrange argument is here, the mutate argument is over here, and the filter argument is over here. This is kind of a mess to come back and look at. R has no trouble, but as humans coming back to look at this, there's going to be a lot of effort involved in parsing this and understanding what it's doing. So do yourself a favor and use this pipe operator, which lets you express this same set as a sequence. So here's an example of this operation using pipe operators. I'm making something called the plot data frame. I like to enclose it in parentheses so that I can put this pipe operator at the beginning of every line instead of at the end. But that's my convention. A far more common convention is to leave off the parentheses and put the pipes at the end of every line, except for the last one. So I start with a data frame. I send it to arrange. I'm going to arrange by registration time so that this function and the argument that impacts how it behaves are right together, right where I can see them, and also on one line together. So it's easy for me to say, oh, I'm arranging it by registration time. Then I'm going to mutate it by making this new column, a cumulative total column. And then I'm going to filter it based on registration time. And then that's the end. So by doing it this way, you end up with one data frame in memory, the result that you care about, and you've documented all the steps that you've taken to perform it in a way that's really easy. I would say the pipe operator is extremely common in the Hadleyverse or Tidyverse collection of R packages. It didn't originate in that package. It started from, someone else developed it. I think that Hadley Wickham realized how powerful this could be for expressing the way that you manipulate data. I'd say it's pretty common, particularly for people that are using the modern R data analysis packages. And probably most common in data science for data manipulation. But it's, when I teach it to other people who are doing, academics doing research, they tend to like it. They adopt it. It's something to embrace. I think it's one of the best features of R. I wish Python had a really good pipe equivalent. There's been some efforts, but it doesn't, the way Python works, it doesn't quite give you the same succinct representation. So essentially the way that this operator works is by making the thing on the left the first argument to the thing on the right. So when I say send my plot df to the head function, that is equivalent to saying, calling the head function with plot df as the argument. So there's printing the first 6 lines. So plotting the data. This is using ggplot. ggplot uses a very similar idea to composing plots out of a sequence of steps. But in ggplot, you use the addition operator instead of the pipe operator. In this cell, I have a set of dplyr commands that are producing a plot, a data frame that's just for plotting. And then I have instructions for creating a plot. I put them together in the same cell so that I always know exactly which plot df I'm using. If you create a data frame up somewhere in some other cell and you modify it later, and you come to run this one to plot it, you may find that it contains different information because you've changed it somewhere else. I think it's good practice to create a new plot data frame and to plot it in the same cell. It keeps you from confusing yourself later. In this case, I'm taking my data frame, the original data frame we loaded, I'm sorting it by registration time, and then I'm filtering it out so that we only look at registrations that occurred after it was publicly available for registration. So no co-hosts will show up in the data. In the plotting code, this time I'm saving the result of the ggplot into a variable. You can do this, you don't have to, but that's what's happening on this line. To make a ggplot, notice that all these lines are commented out. You could ignore them for now. We'll look at them in a moment. But to make a ggplot, I will call the ggplot function. I will give it a data set, and then I will define something that's called the aesthetic in ggplot. The aesthetic tells us how the items in the data relate to plot elements. So this is saying, hey, ggplot, use this data to make a plot for me. And the registration time column is the x-axis. It's actually all we need to start a plot. It's not a great plot because there's no data on it, but there's my axis. It used registration time to make the x-axis. It's nicely labeled. We'll have to put some data on it. And the way we do this is by adding things to our plot. So I want to add a geometry called a histogram to this plot. Because it's a date time, because registration time defines the x-axis, and that's a date time object, the bin width for the histogram is defined in terms of seconds. So this is a 1 day bin width. And I'm going to make this just my window a little bit taller. Please complain in chat if it makes it so you can't see the text. All right. So I've added a geometry to my plot. And so now I have a basic plot. That might not be the one we care about. Maybe we'd like to look at it every 6 hours instead of every day. I could do that too. I can add that right on top of my plot. Or maybe I'd like to see a frequency polygon instead of a histogram. And I'll do that by every hour. So I can compose a plot just by adding these different geometries to the plot. I'm looking at it, maybe I'll decide I like the 6-hour version better, so I can comment out the original histogram. I'll add some other things to the plot. For a ggplot, they support a variety of themes. I happen to like this theme black-white. I think it looks nice, so I've chosen that one. You can choose other themes. Most plots need a title, and you like to label your axes. So adding a GG title, we'll put a plot title. X lab and Y lab will label the axes. And I'll run that one. So that's a plot with all of the major components on it. A nice, the axes. We can adjust our histogram bin sizes to our heart's content. But I've created a plot by making this plot field and then adding elements to it. Very, very similar in idea to how we use the pipe operator to start with something and then modify it successively through a sequence. If you like this style of plotting, yes, if you like this style of plotting, you can use plot9, and you use Python. You can use plot9, which is Python's version of ggplot. It's a clone of ggplot implemented for Python. I find this to be a very fast way to express what I want to see. And if I can do any of my plots in ggplot, I always start there before I go to something more complicated. This 60, so I have a question, what does this mean? This means, because this axis is a date time axis, so it's a measurement of time, the bin width is defined in terms of seconds. So this is 60 seconds per minute, 60 minutes per hour, and then 6 hours. So I'm saying essentially every 6 hours, make my histogram bin width equal to 6 hours. Up here, I was making it equal to 24 hours, so 1 day. And this one is essentially doing it by the hour. So the frequency polygon is binning by hour, and the histogram in the background is binning by the 6 hour. Okay, we'll be alternating back and forth between, I'm going to be short on time here. We'll be alternating back and forth between dplyr and ggplot. I think I'm going to skip that plot. We'll look at this one. This one has some nice features. So going to show a few more features of ggplot first, or of dplyr first. Starting with the data frame, we're going to arrange it, sorting it by registration time. Filter out our registration time so that we're only looking at, I don't want to miss that. Sorry, I'm going to skip back to here. Okay, arrange it by registration time. We're going to filter it out so we're only looking at the first 48 hours. Then we'll plot it. So it's a basic plot. It's a histogram, applied the theme, labeled it. This is one way, we might care about where are these registrations coming from. And to do that in ggplot, we can add to the aesthetic. I can say, well, what I'd like is I'd like to differentiate where these are coming from. So I would like the fill color of my plot to be related to the organization. And by adding that to the aesthetic, each of these elements can look at that aesthetic and they can change how they behave based on me defining this fill color should be related to the organization. That that gave me some more information. It's hard to see what's going on individually with these, and maybe that's what I care about. Also, I might care about maybe making it more colorblind friendly. So there's a colorblind friendly palette. I'd like to see what's going on with Cornell University by itself. It's a little hard to see because it's always stacked on top of someone else. While Cornell has the same issue, but it's even worse because it's stacked on top of Cornell. So it's hard to see the individual stories for registration. ggplot has a nice feature to do this facet wrap, where I can say, okay, break this out by organization and show me what it looks like. This is the first pass at it, so it's giving me one plot per organization instead of one plot with all the organizations combined. Some issues with the plot, probably don't need a legend anymore because we have the labels up here, and that axis is a mess, so let's fix it. So I will set this to false, so there's no legend anymore, and I will modify the theme to rotate the axis text. And there we go. So there's a plot of, this is the registration activity for the 3 different organizations over the first 48 hours. And you can see that while Cornell loaded a lot of registration in the very first day, and Cornell followed with more registrations on the second day. I will look at one last example here. That's what I've got time for. So same idea, start with our data frame, sort it by registration time, filter it out. I'm gonna look at the whole timeline instead of just the one, instead of just the first 48 hours. So and then I'm going to use some new commands. I'm gonna use the mutate command to add a cumulative total. It's gonna be the cumulative total by, each person will get the number of people that register with the first person is 1. When there's 2 people, it's 2. So it's essentially the row number gives us the cumulative total. So I'm making a cumulative total column. And then I'm going to use a very powerful feature of dplyr called group by. Sometimes you want to compute a new variable for your data set with reference to the group that it's in. So I'm going to group my data set by organization. And then I'm going to compute essentially the same thing I did here, but now my data set, currently my data set is grouped by organization. So I'm going to make a new variable called the cumulative group total. And then I'm going to ungroup. And let me show you what that looks like, because I realize that's a lot to wrap your head around at first. So cumulative total is just counting up. The cumulative group total, I got a run of 4 CU folks, so that's 1, 2, 3, 4. Then I got my first other, so they're the first other, so they're number 1 in their group. And then I get a run of wild Cornell folks, and the first wild Cornell is 1 in their group, second one is second. So that grouping allows you to compute things with reference to groups. It's a good idea to ungroup at the end in case you want to sort of put your data set back in a normal state. You can group again and compute something based on a different group if you want. So I will plot that real quick. This one, my aesthetic is now an X for the registration time is the X-axis. The cumulative total is the Y-axis. I used a new geometry called a line, and I applied the usual theme and labels. If I want to also look at the cumulative group total, I can add a little bit to my aesthetic and say that, all right, for this plot, replace the Y with cumulative group total and color it by organization. And then that gives me, I can see the cumulative registrations for each of the organizations separately. 2 things I use a lot, and you probably would like to know how to do them. One is adding annotations to your plot, like adding a line. This draws a horizontal line. It'll be dashed in red. And you may want to add annotations like text to your plot. So I'm going to use these 2 together to indicate a hypothetical course capacity, adding that to the plot. So that's how you would go about adding text and extra annotation lines to your plot. In typical R fashion, ggplot has many extensions. So there's plenty of people that say, oh, I really like ggplot, but I wish it also worked for this other type of plot I wish I like to do. So people have written extensions, and there's a nice gallery of them available here. There is also a nice gallery. The rgraph gallery shows a variety of examples of plots generated in R that have been mostly generated using ggplot. And I think we're at time. I will point you to some of these references. When you're trying to do a particular type of statistical analysis for R, please consider looking at R bloggers, looking at RStudio's educational resources. Google is a good source, despite R being a very short term. If you do analyze some type of data in R or some type of method in R, you still come up with pretty good search results for Google. I want to highlight the web views. This, I'm sorry, the task view available through CRAN. If you are in a particular area like astronomy and you want to know what packages are available for astronomy, you can go to the task view and click on astronomy, and it will show you a list of packages that are used by astronomers. There's ones for different methods and there's ones for different fields. So it's a great way to learn what your peers might be using. And with that, I think I will look for any additional questions in chat. Thank you for joining us today. We're going to send out a survey. We'd like you to complete it, help us work on our presentations. And I want to mention that I have no conflicts of interest associated with this talk. So thank you very much for joining us today.